Hello everyone, welcome to the lecture series on Fundamentals of Generative AI and the Large Language Models. This is Ashwini, tutor for this particular course. And throughout this particular course, we will be learning the concepts on autoencoders, variational autoencoders, generative adversarial networks again, diffusion models. Then once we complete this, we will be having some introduction to sequence models, where we will be learning RNN LSTMs, so that it will act as a foundations for LLMs going forward. Next, after sequence to sequence models, we will learn LLMs, then we look into RAG, then multimodal AI and ethics. So these are some of the concepts that we will be covering throughout this particular 12 weeks course. Along with the theoretical concept, you will also be seeing the hands-on implementation. So before we actually get into the concepts of generative AI, this week 1 we will be completely focusing on the fundamentals of deep learning which are required for generative AI. So these are the following contents for week 1. First, we will understand, so far we have seen in the deep learning concepts, we have seen something called as a discriminative models. So now we will be understanding the shift from discriminative learning to generative learning. Then we will understand what exactly is the generative modeling, what are different types of generative modeling. Then we will look into the probability distribution in generative models. It can be a Gaussian, Bernoulli, or it can be a categorical. Then let us look into some of the applications of generative AI, where all we can see generative AI models. Then before we actually start the contents of generative AI, we will see some of the, we will look into some of the basics such as what are various loss functions that are there in deep learning, what are different activation functions and optimizers, various optimizers that are required in a neural network. Most of the generative AI models which we are focusing in this particular course, some of them are based on CNN. So how CNN works, these generative models architecture also follows a similar pattern. So because of this, we will first look quickly a recap of how CNN works. Towards the end of this particular week, we will look into the hands-on implementation, since in this whole week the key concept here is, of course, we will be seeing some of the fundamentals of generative AI, and then we will look into the basics of deep learning, and we will quickly recap CNN. CNN is very much needed so that upcoming models, if some of the concepts that are based on this CNN, probably it will be helpful for the learners to connect to the concept. So because of this, the hands-on will be based on CNN, and then we will see two hands-on in this particular week. One is building CNN on real-world data set, and the second, how do you build an ensemble model. So these are the contents which we are going to study in this particular week. So let us understand where are we coming from. So if you see, so far we have looked into, this is multi-layer perceptron. This is the architecture of multi-layer perceptron model. So if you see, this particular model works very well if you have an applications such as a classification and a regression problem, and more specifically if we are working on an tabulated data, where you have your data in the form of a CSV file or an Excel file. So on that particular data set, if you want to perform a classification or a regression problem, regression task, then a simple multi-layer perceptron model is sufficient to perform the task. Suppose we have an image data set where our data is an images. So whenever we have an images, and if our task is to do a classification, or if our task is to do a segmentation or an object detection, then probably the most appropriate algorithm will be a CNN, convolutional neural network, mainly in order to understand how the images works, in order to understand the images and then perform tasks such such as the classification, then segmentation or an object detection. And the third model that we have seen so far is sequence to sequence models. So examples for sequence to sequence is RNN and LSTMs, or it can be even GRU. So these are the models which works very well if we have a time dependent data, time series data. What is the main application of this? We can able to predict what will be our next data. If we have a last 10 days data, then we can predict what will be our tomorrow's task, or what will be tomorrow's value. If we have last 10 days rainfall prediction, then we can say what is the probability that tomorrow we get rain. So these are some of the applications that that we have seen in our conventional deep learning concepts. And these are for all of these applications, for all of these models, how is that the data that we have considered? Is it not we had a labeled data set? What do you mean by labeled data set here? We had an sample, and we also had an associated label with this. We had an input and we had an associated label. So and here what is X? X is input, and this input can be an image, or it can be a text embeddings, or it can be a simple tabulated features or time series. It can be any of these. And what is more specifically Y here? And Y here is a label or a target class. So when we say label, it can be an numerical value if it is a regression problem, or it can be some category if it is an class label, if it is an classification problem. So what are these models? Whatever we have seen in this particular slide, take multi-layer perceptron, CNN or RNN LSTMs, all these are discriminative models. So what exactly is discriminative models? Look at these two diagrams here. Discriminative models try to learn to discriminate between the classes. Now if you take, it is a cat and here this is a dog. Now, when we look into this particular data, we can clearly discriminate between these two classes. How are we discriminating? Here I am going to learn the features. Okay, if it is a dog, this is how the features are. This is how the features. So we are going to learn each of these features. And if it is a cat, look at the features here, and definitely the features of this class and this class are totally different. So discriminative models are those models which learn to discriminate between the classes. How? It learns the features. By learning the feature, it is going to separate one output from another output. And it is just not only discriminating or learning the features, it is learning from all of the training data, and for each of the training data there is also a class label associated with it. So because we have features and we have labels, we can able to learn these features, and for each of these features what is its associated class. So this is discriminative model, mainly focusing on discriminating between the classes by learning the features. And for each of these features we have an correct answer already present or already known to us. Now what is one drawback of discriminative models? Its main focus is only to learn the features and discriminate. So it cannot learn how the data was generated, how these features are obtained. So discriminative model never learns how the data was generated. So what is its main aim? Discriminative models mapping input to an output. So if this is a kind of an input that we have, then this is the label. So this is what is the learning. So more specifically, if we have to say what is given this input X, what is the most likely the label or the output Y? What is the probability that you predict Y for a given input X? So this is what a discriminative model does. So one example if you have to take, suppose X is an image. Let us take that the image is a cat image, dog image, and if it is a multi-class, we have an horse also. So then what is that model will give you the output? what is the probability that a given input x belongs to this particular class cat. So the probability is 0.85 or it is 85%. What is the probability that the given input belongs to a dog class? It is 0.10. Similar way 0.05. Horse. So here what exactly from this particular output we are understanding, is it not the model is mainly aiming to learn which class the particular input belongs to, right? So this is what is the discriminative mindset. But today, if you see, deep learning is much beyond these tasks. Today, our focus is just not to give for a given input, classify whether to which class it belongs to. If a patient features are there saying whether there is a disease or there is no disease. If there is a time sequence, time series sequence is present, we want to predict the future value. No, our aim is just not a prediction or a classification. It is just not what is next or which class it belongs to. Then where exactly deep learning today is? So modern deep learning is just not about classification or prediction, but it is increasingly about learning the data distribution. The task is just not discriminating, the task is to learn the data distribution. Now the question comes, why we have to learn the data distribution? So that the model can generate a new, realistic and more statistically similar data. For example, if you have a task, today you can recall from all the applications that we are seeing around, when there is a text prompt, when you give a text prompt, take all the GPT examples, when you give a text prompt, today the deep learning models can able to give us an image based on the text. Then if you give just a text prompt, it can also give a new paragraph based on what the prompt that we have given. It's just not only a text. When we give a damaged data, it can give a complete data. Say for example, I have uploaded my image where it is most of the part of the face is damaged. So it can able to complete that particular image. Next, if you have a noisy data, the model can give a cleaned reconstructed data. If you give an existing samples, it can synthesize new samples. So today the modern deep learning is able to do all of these. So what is the main aim here? The main aim of these modern deep learning models is just not what is the next value or to which class it belongs, but here the main is what new data can be created. Now, so this is all where from how the transition has happened from discriminative learning to a generative learning. Now, from this slide, what are we understanding? Is it not all we need is to create a new data? This is what we are trying to understand. If this is the only requirement that we want to generate a new data, if this is the requirement, then what are the common concepts that we have already seen in our conventional deep learning models? So if you see, if our aim is just to create a new data, what about data augmentation? Right, the learners here may think, so your requirement is to generate the data or to create a data. If that is the case, why not use a data augmentation? Because we have seen from our CNNs that data augmentation can always be used to increase the samples. So when we are increasing the samples, is it not that we have a data that generated? What is that your thought process on this? You can give a thought of this and then you can look into this slide. Data augmentation is definitely one particular fix. But what exactly is happening with the data augmentation? We are not creating any new data here. Whatever is the existing data, that existing data we are looking into different orientations. So probably we are flipping, you take one particular image, you flip that image. So flip can be done either through horizontal flip or it can be a vertical flip. Then rotation. What is rotation? You will take one image and then you will look into this image from a different orientations. So that's a rotation. Zoom. Either you will zoom out or zoom in. Then unwanted, you are going to crop it. And the noise, you are going to, because your aim is to have a new data. So for the existing data, can we create some noise so that it is no more that original data? Can we tell that it's now a new data? So what is the thought process? So from all of these, is it not, look into this particular example, although I have taken it from an internet source, so for a better visualization, when you see all the images that you are seeing here, set of images, it is all a same image but looked in a different orientation. So that is what is data augmentation. It is not learning the underlying data distribution here, how the data is, from which distribution it belongs to. It is not learning anything about the data. It is just visualizing the data, the image from a different view. Okay, then you may immediately think, what about oversampling? This is also one more technique which is used to increase the samples, because our aim here is to get a new data. So if oversampling is one of your option, then what is the drawback of oversampling? Let's look that with an example. If you see here, these are the classes which are where the samples are less in number. So what we are going to do, wherever we have an minority class samples, we are going to increase those samples. So how are we increasing? One direct is just duplicating. So it may either duplicate or we are going to interpolate. So by doing this, we are just improving the count of minority class, but you are not assuring that there are some new variant of the existing data. That assurance is not been given. So if at all, if our thought process is going in this way, that data augmentation, oversampling is anyhow increasing the data, then why do we need generative models? If the thought process is in that direction, then the answer is no doubt data augmentation and oversampling are increasing the samples, but they are increasing from the existing data only, either by different orientation or by duplication. So with this, how can we say that it's a new data? So now when you take an data and if you duplicate it, it will be a similar values. So there is no new learning to the model here. So that is where we are boiling down to a generative model. So generative models or modeling is mainly aiming to learn the distribution of the data, structure of the data, so that the new, realistic and diverse samples can be generated. It is just not duplication, just not variation, but we are creating altogether a new data, and we are creating a new data. That doesn't mean that we are deviating from the original one. No, even though we are creating a new realistic, but still it will be closer to our training data. So I hope this is where we have understood that data augmentation and oversampling does not help. Now, with this, let us formally understand what is the definition of generative modeling. Then you can able to see the difference between discriminative model and generative model. So here the generative model mainly aim to learn the probability distribution of the data. Why it has to learn the distribution of the data? So that its main aim is to create a new samples which are as similar as a training data. Now you can see with the definition, if it is not clear, mathematically you can see. So what is the discriminative model? Discriminative model is what is the probability that for a given input x, it belongs to this particular class. This is what is the discriminative models say. But what about a generative model? The generative model is learning this distribution. What is the probability of the given training samples x? or it is, if at all, if you have unsupervised data where you don't have labels at all, then it is learning the distribution of only the data. No, you have an labels also, then it is learning P of x, y. It is learning both input as well as its labels. So let us understand more what exactly is the meaning of these two probability that we have written. Let us understand this in detail now. So the first one, P of x, what is P of x here? It is an unsupervised generation. What is unsupervised? So here we just have only the data. Look at this. Here is one example where we just have only the data. We have an age, then we have an height, and then width. So we want to understand for a given height, whether for a given age, whether height and width is, height and weight, I'm sorry, not width, height and weight, whether it is proper, whether it's a normal or abnormal or underweight. So this is what we want to understand. So we don't have any of the labels associated with this. All what we have is just the features, that is just the data where we have age, height and weight. So here all of this data we are representing it as x1 till xn. So this is x1 and so on up to xn. Now all this data belongs to some distribution. Do you all agree to this? So what is the meaning of a distribution? This particular data has its own mean and then the standard deviation. Correct. So this entire original data distribution, say let us take this is the original data, the distribution of this original x. Now what is our aim of a model? The model has to somehow learn this distribution. Now, how is that the model learns this distribution? Whenever you take any deep learning model or modern deep learning models, for every of the connection we will have the weights associated with that. Let us assume those weights are theta, or it can be the distribution parameters itself. It can be mu and standard deviation. So what is that? With the help of those parameters theta, the model is learning this distribution. So that learned distribution we call it as P of x. I hope this is clear to you. So the original, whatever the original data that we have, that data distribution we call it as P data of x. Now this is our original data distribution. What is the aim? Aim is to learn this distribution. How is that the model is learning this distribution? With the help of some parameters, and those parameters we are representing it as theta. Okay. Now, what is our ultimate aim after training? The ultimate aim is whatever the learned distribution should be as close as original distribution. Right? When the learned distribution and original distribution are similar, then what is that we can able to do? From this learned distribution, can we now generate a new data? Right? Can we now sample a new data from this particular distribution? So this is what P of x. What is a P of x? Where we don't have labels, we are only focusing on here the data, only data is given without any labels. So and what is the aim? The aim is to learn that underlying data distribution. So that underlying distribution of original data we call it as P of data given of x. And what is the aim of whatever the algorithm that we are taking as part of this generative model here. So the aim of that particular generative model is to learn this distribution. How is that you are learning the distribution? We require some certain parameters. Those parameters we are representing it as a theta. With the help of parameters, it is learning the underlying distribution. Now, once the training is completed, what is our aim? The learned distribution should be as close as original distribution. So that when it is close to original distribution, now whatever the data that you are going to generate, that data will be similar to this original data, right? So this is all is this P of x. And the second one, we have an joint modeling. What is joint modeling? Here the model is given both data as well as labels together. So here we have the original input x, and we have an associated label also. We have this. Now what is that the model is going to learn? And this entire once again belongs to some distribution. Here the aim of a generative model is to learn this distribution. Okay, if so, and how it is learning? It is learning from the parameter theta. So with the help of these parameters, the model is learning the distribution of the given data, and here the data is having both input, that is data, as well as the labels associated with it. So here x is the data and y is the label. Now once the model has learned the labels also, what else we can perform? So we can also perform the classification here. So although we are discussing about the generating data, but when we have the labels also with us, we have learned, the model has learned both data as well as associated label, which means now I know if I have the features like this, I can able to classify it to a particular class. So which means it's a classification problem. So in this, if at all, if the model has to perform the classification, it is going to use the Bayes theorem. What is so is it not, this is discriminative? We have seen from our previous. So what is the probability that the given input belongs to this particular class y? So is it not this is a classification problem? So how is that we are able to do a classification problem? We are going to do with the help of Bayes theorem. So what is that important point you need to understand here is, although we are using aim is generative, but we can also do a classification from this. And next is a conditional generation. What is conditional generation? Based on a particular condition, I don't want all the images to be generated. I want only a particular class image to be generated. Yes, even that is also possible. So it is what is the possibility that if I have an input x, it belongs to this particular label y or a class y. So it generates the data based on the condition. Condition here is you are specifying a particular, just generate only a digit 7 or generate a smiling face, or if you are dealing with an images, what if you have less number of malignancy images, your aim is to generate more malignancy images. So in a medical application also you will have a good application of this particular concept, conditional generation. Okay, so we have understood so far that we have either you can have if it is an unsupervised, if you have a labeled, or based on a particular condition you can able to generate it. So now after you get the output, so now say for example you have a decoder or you have a generator has produced and has given you the output. So that output can be any of this. So what is the first possible output? You can generate a continuous real valued values. What does it mean? Suppose if you have a data set where the input is all a real continuous real values. Say for example you have age, height and weight. So here you have in all these three places you have a numerical value and you have less samples. Now you want more such data to be generated. Then what is that the model will assume? The model is going to give us the real valued output, but here the model is making use of Gaussian distribution. So here in this particular slide, try to understand only this concept. If at all, if your aim is to generate continuous real valued values, then the model is using Gaussian distribution. Why Gaussian distribution? If you can imagine in the going slide, slides you will be seeing Gaussian distribution is a continuous graph. So for continuous data, definitely Gaussian distribution is a good application or a good concept to be used. Suppose if our output is binary, say for example, you are generating, your aim is to generate an binary image or a black and white image where the pixel values are just 0 and 1. Your input image is a black and white image, and ultimately your output also should be a black and white. So here every pixel that you take belongs to either 0 or 1 class, correct? So now whatever the generative models that we are using, that generative model assumes a Bernoulli distribution. So just only remember, try to correlate. If you have a continuous real valued, it is Gaussian distribution. If your output is a binary, then it is a Bernoulli distribution. Just try to remember only these words. You will be able to connect these in the upcoming slides. Next, what if your output is not a continuous value, not a binary, but it has to predict the next word. So you can take any example. So deep learning is. So now the next word the model should predict. So in such a case, you will be going for categorical distribution or multinomial distribution. So try to understand that our ultimate aim is to generate the output, right? It has to generate, after learning an underlying distribution of data, the model has to generate the output. So what are the possible outputs? The possible outputs can be either a real valued, or it can be a binary, or it can be a word. It can be a text application, it can be an image application, or it can be an continuous data. So if it is a continuous data, Gaussian distribution, binary Bernoulli. If it is a word, it is a categorical distribution. Now you can think, if that is the case, in the program, when we are writing an code, when we are implementing, do we use these words like Gaussian, Bernoulli or categorical? Are we using these words when we are implementing? The answer is no. So during implementation, we do not usually, we do not explicitly write Gaussian, Bernoulli or categorical. We don't write any of these. How is that the distribution is actually implied here is with the help of activation function and the loss function. So what different activation functions we use? See, suppose if the model is assuming a Gaussian, which means you are producing an continuous values. If this is your requirement, how is that we write? I'm just showing only the few lines of code. However, you will be seeing this in the hands-on implementation. So how is that we will be coding this? Here the activation what we use is linear activation. Definitely output function should be linear activation, right? Then what should be the loss function? The loss function is a mean square error, MSE. So each output value is treated as continuous value. Then the model predicts the mean of the Gaussian distribution, right? So what, although you may not be able to understand at the first session, but going forward you will be able to understand each of these. Next, if it is distribution is a Bernoulli, then how is that you are going to code it? Suppose if your output is binary, then you are going to write activation as a sigmoid, and the loss function that we use is binary cross entropy. And here each output value is treated as probability of 1. Right? What is the probability that the given pixel belongs to 0 class or the given pixel belongs to 1 class? So here the output is treated as the probability. And what is the combination? Sigmoid plus binary cross entropy. Now what is categorical? Categorical is multinomial. You have to predict the next word. So definitely activation is a softmax, and the loss function that we use is categorical cross entropy loss. So now we have, what is that we have understood from these two slides? What we have understood is, based on what kind of data that we are going to produce as an output or generate as an output, what kind of distribution the model is assuming. This is what we have understood. Now where exactly that distribution is coming into the picture? Let us look into this. When we take types of generative models, we have first seen Gaussian in the last two slides, right? What is Gaussian distribution? The bell curve. This is what is the bell curve for a Gaussian distribution. In this, what are the two parameters that we will have? We will have the mu and then the standard deviation. These are the two parameters that we have with respect to Gaussian distribution. Now, we know that Gaussian distribution means you are going to have a continuous values as an output. Now look into this. We have one of the most powerful algorithm or model called variational autoencoders. In variational autoencoder, where exactly Gaussian concept comes into play. For now, just understand only so much. This is a standard deviation. Okay, so where exactly you are getting? You are taking an input. Input is passed to an encoder, and encoder main aim is to learn the most important features and then give us the latent space. So for this particular first session, only try to understand here encoder is there, latent space is there, in between is where we have the Gaussian distribution concept. So in a variational autoencoder VAE, the encoder maps the input data into the Gaussian distribution in the latent space, and whatever the new data that we have obtained with the help of decoder, so we are going to generate by sampling from this distribution only, from this distribution, whatever is this Gaussian distribution. So what you need to understand is, now sometime back we have understood that to get a real time continuous data, model is assuming the Gaussian. If model is assuming the Gaussian, where is that assumption coming here? So from the encoder to latent space, in between is where we have our Gaussian distribution concept. Okay, so don't worry if you are not able to relate to this, because our upcoming weeks, every week we are studying about each model in depth. Second, this is a diffusion. Now this is the original input image, which is a cat. Now you are adding some noise. Can you able to see some dots? From how is that we have added the noise? We have taken the noise from Gaussian distribution. We have added some more noise, some more noise. How long we have added? Until the image is not at all the backend, the background image. Here the background, the original image is cat, but by the time you come here, cat is not at all visible. The entire image is been we have put the entire we have put the noise into this image. So here, so how this noise is being added is by using a Gaussian distribution. So again the word Gaussian distribution is coming into the diffusion model, and in the reverse process what is happening, you are removing the noise and finally you are generating a new sample. And the third application, if you take, so we have an GANs, that is generative adversarial networks. When you take this GAN, what is the role of a GAN? We have two models, generator and discriminator. Generator has to generate the data, discriminator has to discriminate between whether it's a real image or fake image. If generator has to generate the data, how is that the generator is generating for the first instance? How is that it is generating? So from from a noise vector which is taken from a Gaussian distribution, the generator is generating the data. So this slide you need to only connect where all Gaussian distribution concept coming into the picture. In variational autoencoder we have a Gaussian distribution, in diffusion model we have a Gaussian distribution where noise is derived or noise is taken from Gaussian distribution. In GAN, generator is generating a data and it is generating from the noise, from some vector, somewhere something has to start, right? That something is taken from that Gaussian distribution. So this is what you need to understand. And next we have seen a Bernoulli distribution. What is Bernoulli distribution? We have seen that it is mainly used if at all, if we are generating an if our aim is a binary output. So wherever we have a binary data or binary classification application, the model is going to consider a Bernoulli distribution. And how Bernoulli distribution we are going to write? At the output layer, the activation function and the loss functions are going to differ. And next we have a categorical distribution. What is categorical distribution here? Here aim is to predict the next word. So in a text generation, what is our next word? So there we are going to have a categorical distribution, and we are going to use an categorical cross entropy, and then we will be using the softmax activation function. But thus we have come to an end of this particular session. Before we wind up, let us quickly see, although we have discussed this all through, let us quickly see what are the different applications of generative AI. So aim is to generate the data, right? Now what all possible data that it can generate? It can either generate the text, or it can generate the images, or it can generate the audio or the video files, or it can generate some code. So if you look into, if our aim is to generate the text, then we have also seen throughout our particular 12-week course what all algorithms that we are seeing. We are seeing autoencoders, variational autoencoders, we are seeing GAN, then we will see diffusion models, then we will see sequence to sequence LLMs, then we have the multimodal, then in between we have RAG. So when we have all of these models that we are going to learn, if at all if you are dealing with the text applications, then among all of these models, it is LLMs and transformers which are extensively, yes, transformer you will be studying as part of LLM week. So you will be using these two models extensively when you are dealing with the text application. Suppose if your aim is you are dealing with the images, there is a corrupted image, you want to generate a new image, or a complete image, you have less samples, you want to generate more samples. So whenever you are dealing with just an images, then among these the possible application models that we can go is, we can use either GAN, variational autoencoders, or the diffusion models. So using these models, we can create visual applications. Suppose if our aim is speech, music, or a sound generation, what exactly are these? Is it not a time sequence here? There is a dependency. Whenever we have this kind of an application where you want to generate a new data, once again it is the transformers, or we can go for GANs or variational autoencoders. And the last, if it is a text code generation, we can use any of these models. So from this particular session, we have only touched upon what are the fundamental concepts. We have seen a slow transition from discriminative to generative. Then we have seen what all different probabilistic views we have. Then what all different applications that we can generate. So with this, we have come to this particular session. Thank you.